So this is going to be the third talk by Nicoletta. Right.
Yeah, thank you. Okay, so today I would like to continue with this overview about strong Kähler with torsion matrix on complex manifolds. And in particular, I will focus on nil manifolds and Sol manifolds that, as you will see, they are quotients of special Lie groups. Okay, so I will denote, so with G, a connected and simply connected Lie group. And we will denote with this other G, it's Lie algebra, so Lie of G. So this is the Lie algebra of G that can be seen as the, let's say, the set of left invariant vector fields on the Lie group, or as the tangent space of G at the identity. And just for notation, let me recall the adjoint map. So if X is an element in the Lie algebra G, add X will be an endomorphism of the Lie algebra, so it goes from G to G, and it's defined in this way. So add X applied to an element Y is defined as the commutator of X and Y, okay? So just keep in mind this notation, this standard notation. Okay, so let me give you the definition of nilpotent and solvable Lie group. Okay, so well, so let's start with G is a Lie algebra. So we have the Lie bracket on G. So this is when this is a Lie algebra. We can define the so-called descending central series in this way. So, well, we can set, if you want G0 to be the Lie algebra itself, G, then we define G1 to be the commutator of G and G. So in G1, we have commutators of elements in the Lie algebra. And in general, we will define Gi to be the commutator of G, the whole Lie algebra, with the previous space, so Gi minus 1. This is for I greater or equal than 2. And in a similar way, we can define the so-called derived series. So again, you can start with the whole Lie algebra and define G1 in the same way, okay? So the commutator of G and G. But then we can define Gi in this way. Instead of taking the whole Lie algebra here, we take Gi minus 1. And again, the commutator against Gi minus 1, okay? For E greater or equal than 2. Okay, so a Lie algebra is called nilpotent, or respectively solvable, if there exists K natural number such that in the nilpotent case, the first series vanishes for at the step K, okay? If there exists K such that Gk is equal to 0, and respectively for the solvable case, for the definition of solvable Lie algebra, we have that the derived series trivialized at step K. Okay, and if in addition, let's say G K minus 1 is non-trivial, so at the previous step, we still have something, and similarly in the other case, so respectively G K minus 1 is non-trivial, then G, so the Lie algebra is said to be K step nilpotent. So K-step nilpotent means that K is exactly the smallest index here, such that GK is trivial, okay? And similarly, in the other case, we speak about K-step solvable. Okay. And so this is the definition for the Lie algebra, but of course, a Lie group G is said to be nilpotent, or of course, respectively again, solvable, if its Lie algebra is nilpotent or solvable. Okay. So Lie group is nilpotent when its Lie algebra is nilpotent, which means that the descending central sequence vanishes at some step, okay? And the nilpotency step for the Lie group is the same nilpotency step that we have for the Lie algebra. And just a remark, you can check immediately using the definition that nilpotent Lie algebras are solvable. Okay. So the definition of solvable Lie algebras is more general than the one of nilpotent Lie algebra. Okay, so just a few remarks about geometric structures on Lie groups, especially left invariant geometric structures on Lie groups. So a left invariant almost complex structure on G, so on the Lie group, can be identified with a linear map. So that we denote again with J on the Lie algebra itself, such that J squared minus the identity. Okay, so left invariant objects on the Lie group can be identified with objects at the level of the Lie algebra. Okay, so in particular, a left invariant almost complex structure on G can be identified with an almost complex structure on the Lie algebra. And J is integrable if the Nicoletta tensor vanishes, which means that the commutator of Jx, Jy minus the commutator of xy minus j the commutator of jxy minus j the commutator of xjy is equal to 0 for every element x and y in the Lie algebra G. Okay, so we have the standard integrability condition for the Nicoletta tensor to vanish. Okay, and moreover, we can decompose the complexification of the Lie algebra GC, which is the tensor product of G, with C, into subspaces, say G10 plus G01, which are where G10 and G01 are the plus I and, let's say, respectively, minus I eigenspaces of J. Okay, because since J squares to minus the identity, the eigenvalues of J, if you extend J to the complexified Lie algebra, the eigenvalues are I and minus I. And so GC decomposes as the direct sum of the two subspaces. And this is true when J is just almost complex, okay? You don't need integrability for this decomposition, okay? But we have that J is integrable if and only if G10 is in fact a subalgebra. Okay, it's not just a subspace, it's a subalgebra of GC. Okay, because the commutator of two, let's say, let me call them vectors, of two vectors of type 1, 0 is again a vector of type 1, 0. Okay. And similarly, so this is for the complex structure, but similarly for Hermitian metric, so similarly, a left invariant Hermitian metric G on the Lie group, let's say G with the complex structure J, is completely determined by an inner product so let me call this with this G, so on the Lie algebra, such that we have the compatibility condition, so G of J is exactly just G, so J is an isometry, okay? So essentially, left invariant object tensors of what every type, okay, that you have on the Lie group are determined by objects just on the Lie algebra, okay? So this is very nice because this means that actually we can leave the Lie group and we can work using just linear algebra tools, okay? Because we work at the level of the Lie algebra, okay? So, okay. So now let me recall the definition of nil manifold and Son manifold. So suppose that we have G, a connected, simply connected Lie group. And suppose that G is nilpotent or solvable, one of the two. And suppose that you have a lattice in G. So this is a lattice, which means that gamma is a discrete subgroup such that the quotient of G over gamma is compact. Okay, so this is a lattice. Then M, so the quotient of G over gamma, will be called nil manifold, or in the second case, solved manifold. So you start with a connected, simply connected group, and you assume it's nilpotent. And if you quotient this nilpotent group by a lattice, what you get is a compact manifold that is called nil manifold. And the same definition can be done in the solvable case. Okay. So just let me say that it's not an easy job to find if lattices exist, okay? So there are, in the nilpotent case, we have a kind of simple criterion to understand whether we have a lattice. So let me just recall the following theorem of Malchuk in 49. So if G is connected and simply connected and nilpotent Lie group, then there exists a lattice gamma in G. So this means that you can construct a nil manifold in the end. So if and only if we have a lattice, if and only if the Lie algebra of G has a basis for which the structured constant are rational. So in the nilpotent case, we have really an equivalence. I mean, we are able to understand, looking at our Lie group, if we have a lattice or not, okay? We have to look at the structure equations. In the solvable case, we don't have any characterization for the existence of lattices, okay? So in the more general case of solvable Lie groups, we don't have anything similar, but still we have some necessary conditions. So let me just recall this proposition due to Milnor in the 76 that says that, okay, so again, we have a connected and simply connected solvable Lie group. Okay, so now G is solvable. Then if G has a lattice, which means that you can quotient G with this lattice and you can construct a solved manifold. So if G has a lattice, then G is unimodular, which means that the trace of the adjoint map, so the adjoint map was the map that we defined here at the beginning. So it's this map. It's the, let's say, add of X applied to an element Y is the commutator of X and Y. So the trace of this map is 0 for every X in G, in the Lie algebra, okay? So this means that G is unimodular, and moreover, has a B-invariant volume form. So invariant both from the left and the right, so B-invariant volume form. And that's it, we don't have a sufficient condition. We just have this necessary condition. So if you want to construct some manifold, at least your Lie group has to be unimodular, for otherwise you are not able to find a lattice. But it doesn't mean that if your Lie group is unimodular, then you are able to construct some manifolds, okay? Unfortunately, we don't have a characterization. Okay, so now that we have these quotients, so let me just say that an invariant complex structure on an Nil manifold, or if you prefer a solved manifold more in general, G over gamma, is just a complex structure that is induced by a left invariant complex structure on G. Okay, so you have this quotient G over gamma that is a manifold, and an invariant complex structure on this manifold is just a complex structure that is induced by a left invariant complex structure on the Lie group, or equivalently is induced by a complex structure on the Lie algebra G, okay? And similarly, similar definitions of invariant metrics, invariant tensors can be given in the same way, okay? Similar definitions can be given for invariant metrics, invariant forms, so differential forms, and so on. Okay, so invariant means that they come from a left invariant structure that was on the Lie group. So, and this left invariant structure on the Lie group actually is nothing but a structure, a geometric structure on the Lie algebra. Okay. Okay, so why Nil manifolds and solved manifolds are important? So why am I talking about these Nil manifolds and solved manifolds? So why Nil manifolds and solved manifolds are important in non-Kähler geometry? because in these lectures, I'm talking about this matrix called SKT matrix that are a generalization of Kähler matrix, so they are non-Kähler structure, okay? So why I'm talking about nil manifolds and Sol manifolds in this course? Well, because first of all, we have this theorem of Benson and Gordon in 88, and also I should mention Hasegawa, 89. So that says the following. So an nil manifold is scalar, which means that a nil manifold, so this quotient with an nilpotent group, admits a Kähler metric if and only if it is a complex torus. So what I'm saying is that if you have a nil manifold that is not a torus, for sure, your nil manifold will not admit any Kähler structure, any Kähler metric. Okay, so that's why they are important in Kähler geometry, because except for tori, when you work on nil manifolds, you know that you cannot have Kähler metrics, so you cannot have this very strong structure. So you can, but you can hope, you know, to find other structures like SKT matrix, or if you want balance matrix, locally conformally Kähler matrix, and so on. Okay, and in fact, let me just say that also Bowes and Cortez generalize this theorem, so generalize this theorem to completely solvable Sol manifold. Okay, so you see this theorem is true only for nil manifolds, but in fact they generalize this theorem to a special class of Sol manifolds that are called completely solvable. So this means that the adjoint map has only real eigenvalues. Okay. So the same theorem holds in this case, actually. In the solvable case, in the general solvable case, we have a theorem also by Hasegawa in 2006. He proved that a Sol manifold has a Kähler structure if and only if it is a finite quotient of a complex torus. So it's not a complex torus, but it is a finite quotient of a complex torus, which has the structure of a complex torus bundle over a complex torus. So in general, we don't have just tori, okay? But still, you see, when a Sol manifold has a Kähler metric, then it has a very specific structure, okay? So that's why when, at least for people who are interested in studying, you know, complex manifolds with no Kähler structure, with no Kähler matrix, a good, you know, source of examples is provided by nil manifolds and Sol manifolds, okay? Because nil manifolds are not Kähler unless they are tori, and Sol manifolds, when they are Kähler, they have this very special, you know, construction. Okay, so in particular, for instance, for us, if we are interested in finding examples of SKT matrix, nil manifolds and Sol manifolds are a good, you know, place to look for this matrix. Okay. Okay. So of course, you cannot expect this kind of theorems for, you know, weaker conditions. I mean, for SKT matrix or balance matrix and so on. Okay, but still, the existence of special metrics on nil manifolds and Sol manifolds, you will see that gives again some restrictions on the manifold itself. Okay, but first of all, I would like to recall this theorem of Garthe in 2007, because I talked here about considering just invariant structure. So invariant complex structure, invariant matrix, which means that in the end, they come from the Lie algebra, okay? Because they are invariant in the quotient, so they come from a left invariant structure on the Lie group, which comes from the Lie algebra. But there is this interesting result of Garthe that says that assuming that you have, let's say, an SKT metric that is not invariant, ensures that anyway you have an invariant SKT metric. So let me explain this a little bit. So suppose that you have G over gamma, let me say a Sol manifold, okay? With an invariant complex structure, okay? At least the complex structure has to be invariant. Okay, suppose that you have an invariant complex structure on a Sol manifold. And suppose that we have G, an SKT metric on M. That in general, so I'm not assuming that this is an invariant SKT metric. I'm not assuming that this structure, this metric comes from the Lie group, okay? I mean, from a left invariant metric on the Lie group. Then Garthe proved that there exists an invariant SKT metric, let's say G tilde, because it will be a different metric on the manifold. So somehow what I'm saying is that if you have an invariant complex structure, it's not, let's say, a strong assumption to assume that also the metric is invariant. The SKT metric is invariant, because if it's not invariant, so if G is just an SKT metric, an arbitrary SKT metric, then there exists an invariant SKT metric, okay? And so let me just briefly tell you the idea of the proof of this result. So what is the idea? The idea follows, so this follows from a symmetrization process. That is due to Belgun in 2000. And actually, now we're going to see what this symmetrization process is, but a similar result holds if you, instead of taking an SKT metric, you take, I don't know, other kind of metric like balance metrics, for instance. You have the same result. But in this case, so in the SKT case, what we have that by Milnor, the result I mentioned above, since we have a lattice, because I'm assuming that my manifold is a Sol manifold, G over gamma, so gamma exists, we have a lattice, then Milnor, you see, is saying that then G has a B-invariant volume form if we have a lattice. So by Milnor, so let's say nu be a volume form, so the B-invariant volume form on M induced by a B-invariant 1 on G. So after rescaling, we can suppose that M has volume 1. So let me do this in general. So given any covariant K-tensor field T going from vector fields in R, sorry, yeah, I'm still on the manifold on C infinity of M on M. So if you have any covariant K-tensor field on the manifold, we define a covariant K-tensor. So let me call this T tilde on the Lie algebra. So on G. In this way. So T tilde of x1, xk, where x1, xk are elements in the Lie algebra, is defined as the integral P in M of P. So T is the tensor field that we have on the manifold, on x1 in P, xk in P, with the volume mu. So this is the B invariant volume. So where we said x1, xk are element in G, where what are these xj at the point P? So this is the value at the point P in M, so on the manifold, of the projection on M of the left invariant vector field xj on G. Because the Lie algebra can be identified with the left invariant vector fields on the Lie group, and then you project this on M, okay? And you take these vector fields computed in P. So why one is doing this? So the idea is that you start with an arbitrary tensor on the manifold, and you construct a new tensor now that is on the Lie algebra. And the interesting fact is that if T is a form, so let's say it's a K form on the manifold, then this symmetrization process commutes with the differential. So what I'm saying is that alpha is an arbitrary K form. I apply the differential. And then let me say with this tilde, I denote the symmetrization, so the symmetrized element. Then this is like taking the D of alpha tilde. So you take alpha, you apply the symmetrization process, and then you apply the differential. So you see, we have commutation with the exterior derivative. So this is very nice because you see what it was saying the theorem. You have an invariant complex structure, and you have an arbitrary metric that is SKT. So what does it mean? So if omega is SKT, so the metric is SKT, it means that, if you remember, DDC omega is equal to 0, which is equivalent to say that DJ D of omega is equal to 0. So this is equivalent to having an SKT metric. But since J is invariant, so this is crucial, that you have to assume that the complex structure is invariant. It means that if you take J of an arbitrary form, so let's say again with the same notation alpha, and you apply the symmetrization process, so tilde, this is commuting with J. So it's like taking J of alpha tilde. So you symmetrize alpha, and then you apply J. And this is because J is invariant. Then dJ D of omega tilde. So I start with omega that was SKT. And then I apply this symmetrization process, and I find an element that now is invariant. And I apply DJD. What did we say? We say that this symmetrization process commutes with D, but it also commutes with J because of this last part. So this means that it's like having dJ of the omega tilde, but then it's like having D of J d omega tilde. And so finally, this is like having dJ d omega tilde. But now dJ d omega was 0. So you see omega tilde is SKT. So the idea is this. So if you start with an invariant complex structure, if you have an arbitrary SKT metric, then you can find an invariant SKT metric. Okay, so something that lives on the Lie algebra. And a similar argument can be done for other special kind of metrics like balanced metrics. Okay. All right, so just a remark that invariant metrics on, say, let's say solved manifold, on G over gamma solved manifold, are always Gauduchon. So the first day we mentioned that we have this kind of matrix that satisfies this equation, DDC omega n minus 1 equals 0. Gauduchon. So, and these matrices always exist. On every compact complex manifold, they always exist. And in fact, if you have an invariant metric, then it will always be Gauduchon. This can be proven directly using the Lie form. Okay, but probably we will not see the proof today, but they always are Gauduchon. So why am I saying this? Because if n is equal to, then what does it mean? It means that every invariant metric is SKT, because the SKT condition is DDC omega equals 0, but you see if n is equal to, so if we are on a surface, DDC omega is equivalent to give the Gauduchon condition, okay? And so they are Gauduchon, okay? So this is a consequence of this previous statement. Okay, so this means that we have a lot of examples. You just take a solved manifold in dimension 2, and every invariant metric will be SKT. So now let me just briefly construct another example in higher dimension of an SKT metric on an Hill manifold. So we take G, so as the product, so H3 times H3, where this is the Heisenberg Lie group. So H3, let's say, yeah, say H3 is the set of matrices of this type. So we have one on the diagonal and X, Y, Z in the upper part of the matrix. X, Y, Z are real numbers. So this is the Heisenberg Lie group. Sorry. Again, some problem with the pen. I'm sorry, just 1 second. Okay, let me do again this. Let's see if it works. Okay, so let me share the screen again. Okay. Okay, so I'm taking the product of the Heisenberg group with itself, and let's say, okay, so let's say gamma prime is the set of matrices with the same structure, where the entries, say X, Y, Z, now are integers, X, Y, Z, and Z. Okay, and consider M to be the quotient of G over, let's say, take gamma to be gamma prime times gamma prime. So it turns out that this is an Hill manifold, and the Lie algebra, so let's say the Lie algebra I'll say G of the Lie group G has a basis, say I from 1 to 6, with this structure equation. So the commutation relations are given by the two commutation relations that we have on the Heisenberg group. And you can check that we have E1, E2 equal 3 in the first Heisenberg group, and E4, E5 in the second. So if EI with upper index now I, we denote, so this denotes the dual basis of one forms. From this formula for the differential, so if alpha is a one form, then the alpha applied to two elements is equal to minus alpha of the commutator of these two elements. Okay, so using this formula, you are able to start from these commutation relations for our elements in the Lie algebra G. We are able to find the dual structure equation. So D1 is 0, DE2 is equal to 0, and then we have DE3 equal to minus E1 wedge E2. Then we have DE4 equals 0, DE5 equals 0, and DE6 equal to minus E4 wedge E5. Okay, so we have these structure equations for our basis of one forms. And so if now we want to define an SKT structure, so we want to define first a complex structure and then an SKT metric. So set J applied to E1 equal to E2. And so since J squared is minus the identity, J of E2 will be minus E1. And then define J of E4 equal E5. And so J of E5 has to be minus E4 because we want J squared to minus the identity. And finally, J of E3 equal to E6. And so J of E6 equal to minus E3. Okay, so this defines a complex structure. You can check, sorry, an almost complex structure. You can check that it's integrable computing the Mie-Noise tensor. Otherwise, you can set as a set of 1-0 forms, Phi1 given by E1 plus I E2, Phi2 defined as E4, because I'm looking at this, and so you can define Phi1 as E1 plus I E2, Phi2 E4 plus I E5, Phi3 as E3 plus I E6. And this is a coframe of 1-0 forms. They have type 1-0 with respect to the complex structure, okay? Because in fact, J of E1, okay, with the upper index, this is a one form, is equal to E2, and so on, okay? And so if you compute the differential of Phi1, it's the differential, you see, of E1, E2. But E1, the differential of E1, E2 is equal 0. Okay, so which means that Phi1 is closed. And similarly, also dphi2 is equal 0. But dphi3, you can check that it's not 0, okay, because it's the differential of E3 and E6, and they are not closed. And you can check that this is minus I over 2, Phi1 wedge Phi bar 1, plus 1 over 2, Phi2 wedge Phi bar 2. And so take as omega the following metric. You can write it in both in the complex way or in the real way. So in the complex way, I'm taking I over 2, the sum of j from 1 to 3 of phi j wedge phi bar j. Or if you prefer, this is E1 wedge E2 plus E4 wedge E5 plus E3 wedge E6. this is an Hermitian metric compatible with the complex structure. And you can check that this is SKT. So delta bar omega equals 0, or equivalently, dj d omega equals 0. Okay, I want to show you this, so I will do the computation for this, okay? But you can do this also delta bar omega using the complex structure equation that you have here, okay? So let me do this. So let me compute dj d omega. So this is dj of d omega, but you see from the structure equation, E1, E2, E4, E5 are closed. Okay, I see this from here. So here, E1, E2, E4, E5 are closed. So this is just like the differential of E3 wedge E6. Okay, so what is this? So dj of the differential of E3, and you can check the differential of E3 is minus E1 wedge E2 wedge E6. I'm applying the Leibniz rule. So then I have minus E3 wedge the differential of E6, but the differential of E6 was minus, so I have a plus, if what it was E4, sorry, wedge E5. So now I have to apply J. So this is D of J. So minus J is applied to each element plus JE3, wedge JE4, wedge JE5. But D of minus, so J of E1, E2 is equal exactly up to E1, E2, okay, because 1, 2 was preserved. And the J of E6 is minus E3. So here I have E3. And then again, J applied to 3, 4 is invariant. So this is E3 wedge E4. Sorry, here I have a J. And then J applied to E5. But J applied to E5 was minus E4. Sorry, it's the opposite. So J of E3 is E6, but J applied to E4, E5 is invariant. So this is, okay, now makes sense. But now if I apply the differential, E1 and E2 are closed. And the differential of E3 gives minus E1 wedge E2. So the first part is 0. And similarly, here, the differential of E6 is minus E4 wedge E5. So this is 0. And then E4 and E5 are closed. So this differential is 0. Okay? So which means that omega is SKT. And so this M given by G over gamma is an Ill-manifold with SKT structure. Okay, of dimension 3 is an Ill-manifold of complex dimension equal 3. Okay. In fact, Ill-manifolds of dimension, complex dimension 3 are somehow characterized, it's characterized on the existence of SKT metric on Ill-manifolds of complex dimension 3. Indeed, we have this theorem due to Fino, Parton, and Salomon in 2004 that says that if M is so 6-dimensional, I mean the real dimension, okay, 6-dimensional Ill-manifold. So this is the real dimension, okay. Ill-manifold with an invariant complex structure and Hermitian metric G, then JG is SKT if and only if there exists a basis of 1-0 forms. Let me call this alpha I, such that the differential of alpha 1 and alpha 2 is equal 0. And then the differential of alpha 3 is equal to A. So let me do this. I will denote with alpha I j bar the wedge product of alpha y wedge alpha j conjugated, and so on, okay? So A of alpha 1 bar 2 plus B alpha 2 bar 2 plus C alpha 1 1 bar plus D alpha 1 2 bar plus E alpha 1 2. With this condition, the modulo of A squared plus mod of D squared plus mod of E squared plus 2 times the real part of B conjugate C is equal 0. Okay. So what is saying this theorem? That if you have an Hill manifold of real dimension 6 with invariant Hermitian structure, the structure is SKT if and only if there is a basis doing this, okay, with some particular structure, okay? So for instance, in our example, in the example above, we have these structures with A equal D equal E equal 0, B is minus 1 over 2, and C is minus I over 2. Okay, you can just check that the example that we just mentioned here falls in this set of examples because it was an Hill manifold with an SKT metric. Okay. So what is saying why this result is important? Because you see here on the left of the equivalence, we have a metric. We have G that is an SKT metric. But on the right, we have just something that depends on the complex structure. It doesn't depend on the metric. So you see on the right-hand side of this equivalence, there's no metric involved. There is just a basis of 1-0 form. So 1-0 with respect to the complex structure. Okay, and then we have the structure equations that depends just on J. So this result is saying that the existence of XKT metric in this case, so in this case of Hill manifolds in 6 dimensions, is encoded in J. So everything is encoded in J, which means that on M6J, either all metrics are SKT or there are no SKT metrics. Okay, because the information is all contained in the complex structure. So which means that either all metrics are SKT or there are no SKT metrics on the Hill manifold. Okay, so in particular, in the example we showed here, I constructed this specific metric and it was SKT. But in fact, any other invariant Hermitian metric that I could have chosen would have been SKT, okay? Because of this result of Finoparton and Solomon, okay? And this result is specific for SKT metrics, and it is specific in dimension 2, in dimension 6, okay? In higher dimension, so in higher dimension, already in dimension 8, actually. So in higher dimension, this result doesn't have an analog. Okay, so it's false. Okay, let me say it's false, meaning that you can find 8-dimensional Hill manifolds with SKT metrics and metrics that are not SKT. Okay. Another remark. All these Hill manifolds are two-step nilpotent, which means that the commutator of G with the commutator of G and G, this is 0. This means nilpotency at step 2, okay? So in the example, one can check that all these nil manifolds of dimension 6 that admit an SKT metric are all two-step nilpotent. And in fact, it was conjectured, so the conjecture of Fino-Vezzoni was saying that if of any dimension, say real dimension to n, J is a nil manifold with an invariant complex structure, and Mj admits an SKT metric, not necessarily invariant, but we said that thanks to the result of Ugarte, we know that there exists also an invariant SKT metric. Then M is two-step nilpotent. So it was somehow conjectured that the presence of an SKT metric on a nil manifold would force the nilpotency step to be 2. So it's not like the result for Kähler metrics on nil manifolds that forces the nil manifold to be a torus. Okay, it's not as strong, of course, but still the presence of a special metric is given restriction on the nil manifold. Okay, and in fact, this result is true, and it's now a theorem. It was proven last year by Arroyo and Nicolini. So this is in fact now a theorem. Okay. I mean, there were many evidences. This result was kind of, proved with some additional condition, but now it's proved. It was proved by Arroyo and Nicolini in full generality. Okay, nil manifolds in any dimension. If you have an SKT metric, the nil manifold is, the nilpotent group is two-step. Okay, so let me just say a few words about the solvable case, okay? Of course, in the solvable case, we don't have anything like this. Let me just say, so just do a list of few things that we know. So in the solvable case, we have, so by Madsen and Swan, we have a classification of 6-dimensional solved manifolds, sorry, 4-dimensional, of course, 4-dimensional solved manifolds with a SKT metric. So we have a classification in very low dimensions, so in dimension 4. Then Fino, Otal, Ugarte classified 6-dimensional solved manifold with J invariant and holomorphically trivial canonical bundle and also there are some classification due to Fino and Paradiso 2021 for, let's say, almost a billion Lie groups. So let me just say that they treat the case of almost a billion Lie groups, which means that the Lie group has, the Lie algebra has a codimension 1, a billion ideal. So let me just conclude also by saying that, in fact, another result that we proved with Fino and Vezzoni okay, the pen stopped again. Okay, let's see. Sorry again. Let me just reopen the file just to conclude. So with Fina and Vezzoni, we proved that, in fact, also, maybe you start with a Sol manifold. So suppose that you have G, a unimodular Lie algebra, unimodular Lie algebra, which is not a strong assumption because in the end, I want to construct a Sol manifold. So in the end, I want the Lie algebra to be unimodular because it's a necessary condition. So assume that G is unimodular. And suppose that we have, so endowed with an abelian complex structure J. What does it mean, abelian? It means that the Libracht is invariant by J. So the commutator of Jx and Jy is equal to the commutator of X and Y. And this is for any element in the Lie algebra. Okay, so this complex structure have been studied. They have been studied in relation to many special Hermitian metrics. In particular, we studied this complex structure in relation to SKT metric. So suppose that we have an SKT metric G. So we have a unimodular Lie algebra with an abelian complex structure and an SKT metric. So abelian complex structure implies that G is in fact two-step solvable. So this is implied by having an abelian complex structure. So we are in fact on a solvable Lie algebra. Then what we proved is that if you have this J and you have this SKT metric, actually G is two-step nilpotent. So you fall again in the nilpotent case if you combine SKT metrics with some nice complex structure. Just to say that we had to prove two-step nilpotency because it's not for free, even though the Lie algebra is two-step solvable. And it was not for free because at that time we didn't know that the conjecture of Fina and Vezzoni was true. So we didn't know that SKT implies two-step on Lie manifold. So we had to prove two-step in this case because Arroyo and Nicolidi hadn't proved the result at that time. Okay, and yeah, so as a consequence, so what does it mean, this result? It means that if M is a Sol manifold with an invariant abelian complex structure J and an SKT metric G, maybe not invariant. Again, you can just assume that J is invariant, but you assume that there exists an SKT metric. And so, thanks to the result of Garte, you know that there exists an invariant SKT metric. And so you can apply this result because everything is invariant at that point. So you can work at the level of the Lie algebra when everything is invariant, okay? And so this means that then M is a two-step Nil manifold. Yeah. And yeah, so I think I can stop here. Thank you. If you have any question.
All right, thank you very much. Any questions?